What is diffraction? In simple terms, it is the bending of light around objects or obstacles. Imagine the yellow line as a light wave traveling from a lit room, which then hits an obstacle. One might think that light would go straight towards the dark room as shown, but this is not what we would observe. How the light propagates to the dark room can actually be explained by Huygen's principle, which states that each point on the wave hitting the obstacle becomes a spherical wavelet source, and that the sum of these wavelets form a resultant wave, which then propagates forward in space. In effect, the wave which hit the obstacle got diffracted. What then do we see on the opposite wall? Or similarly, we may ask, how do we compute for the diffraction pattern seen on the opposite wall? We make use of the Rayleigh-Sommerfeld integral equation. First, let's define some helpful terms. The aperture plane is where the obstacle is. The light field originating from this location is a function of the coordinates and is denoted as u of x, y, and 0. Next, the observation plane is where the opposite wall or the opaque screen is, which sees the field at a distance z from the aperture plane. The field is then written as u of x, y, and z. The Rayleigh-Sommerfeld integral equation is a solution of the Helmholtz wave equation derived from Maxwell's equations. To compute this, we first construct the complex light optical field. Programmatically, this is usually a binary image of the aperture or obstacle, which is the amplitude term multiplied by a phase term. Then, we take its two-dimensional Fourier transform, or 2D-FT. This process decomposes the field into a two-dimensional angular spectrum of plane waves, each traveling in a unique direction. Next, we multiply each point in the 2D-FT by a propagation term. This step accounts for the phase change that each plane wave undergoes as it travels towards the observation plane. Lastly, we take the two-dimensional inverse Fourier transform of the result to produce the light field over the observation plane. In this compressed form of the equation, the optical transfer function g accounts for the propagation, where p and q are the corresponding Fourier space coordinates. To obtain the diffraction pattern using multiple wavelength illumination, using the red, green, and blue wavelengths, we first compute the Rayleigh-Sommerfeld integral equation individually for the three wavelengths, and then we concatenate the results to obtain an RGB image of the diffraction pattern. Using the Rayleigh-Sommerfeld formulation, what does the pattern look like for various apertures and obstacles? Here we show the diffraction pattern using a red light source for different letter-shaped apertures, as seen over a screen which moves farther away from the aperture. On the right, we used red, green, and blue sources and superimposed the results. Observe how the colors separate as the screen is moved away from the aperture. We can also look at the diffraction pattern produced by a razor blade, which is usually found in textbooks. The pattern produced by a single slit, again using three colors, and by a double slit aperture with the same slit widths as the single slit. We also took a line scan profile for the single and double slit diffraction patterns, as shown on the right. All of these seem to be acceptable, but how do we check if the results are correct? For the single slit diffraction pattern, we looked at the distance from the central maximum to the first diffraction minimum for each color, and we can say that the simulation results agree well with the analytical results. For the double slit, we can take just the blue pattern for brevity and overlay the blue light source single slit diffraction pattern on it. We then count the number of fringes inside the central diffraction maximum, which is 6 on either side and 1 at the center, for a total of 13 bright fringes. This result also agrees well with the analytical result. Finally, As a special application of diffraction, we use a double helix shaped obstacle, which is the structure of the DNA. According to a journal paper, the pitch of the helix strands should be equal to the pitch of its corresponding diffraction pattern as shown. We verify this by constructing two DNA samples, one with pitch equal to 33 degrees and the other with pitch equal to 20 degrees. Here are the resulting diffraction patterns for each. For both samples, the given rule for the double helix structure pitch were followed. In summary, we've learned that the Huygens principle qualitatively describes diffraction. We discussed how the Rayleigh-Sommerfeld integral equation is implemented. We computed several aperture diffraction patterns and verified the results for the single and double slits, and we have shown how the DNA structure can be derived from its diffraction pattern. Thank you for watching.